SwayamPrabha. Digital India. Educated India.
So, good morning everyone. So, we were discussing this function Andreev function last time, and the target was to show a lower bound on this function, to show that any formula computing this function will have size at least n to the power 2.5, slightly less than n to the power 2.5. So, let me quickly recall what the function was. So, the function takes two arguments x and y. We break down x into log n many rows. Okay. So, we look at log n many chunks of x, n log n many of them, and for each chunk we take the XOR of all the bits in that particular chunk, and we get a string z of size log n. Okay. Now, we use the string z to look at a bit in y. Okay. So, z acts as a pointer to a bit in y. Okay. So, it is a index to a bit in y, and whatever that bit is, so that is going to be the output of the function a n x comma y. Okay. Now, because both x and y, so and the thing is that here both x and y have size n. So, any index in x any index in x or y, whatever. So, we are looking at only y here, any index in y can be pointed by a string of length log n. Next, we saw that by Riordan-Shannon's theorem, we know that there exists a function of on log n variables, okay, whose size is at least, whose formula size is at least n over log n. That is the just a straightforward application of the theorem. Now, suppose we look at the truth table of that function. Okay. So, this is a function on log n variables. So, the truth table will have n many rows, and let y star be the value of the truth table. Okay. So, for each row what is the value? So, y star is now a string on n, I mean it is a string of length n. Okay. And we define a new function a n star, okay, which is basically a restriction of the function a n. The way it is defined is that a n star of x, it is a function on one variable, is a n of x comma y star for this specific y star. So, the reason why we are doing this is because okay, ultimately we want to show a lower bound on the formula size of a n, but because a n star is a restriction of a n, showing a lower bound on the formula size of a n star will also suffice for us. Okay. So, that is what we are going to show, that we will show a lower bound on the formula size of a n star, that will give us lower bound. So, we will show a lower bound on the formula size of a n star, and that will give us this bound. So, how do we show a lower bound on the formula size of a n star? So, again the way we will show a lower bound is by looking at random restriction. Okay. So, we will try to see how we can apply Subotovskia's theorem. Okay. So, recall that Subotovskia's theorem says that if you look at a random restriction, then we can characterize the expected size of the formula for this restricted function in terms of the size of the original formula. Okay. So, we will try to see how we will do that. So, consider a restriction of a n star that leaves m equal to 2 log n times log n variables free. So, it has a total of n variables a n star, we are looking at a restriction that is restricting everything, but it is leaving just these many variables as free. Okay. Now, let us try to analyze. So, now we will try to analyze the probability. So, the probability that one free variable is is not in row I is how much. Okay. So, let us look at, so I am just skipping a step here. So, what is the probability that if one free variable, so fix any free variable, what is the probability that that free variable is in row I? So, how many rows do I have? So, I have log n many rows. So, the probability that any free variable is in row I is 1 over log n. Okay. So, the probability that it is not in row I is equal to 1 minus 1 over log n. Okay. Now, the probability that none of the free variable is in row I is how much? Okay. So, I have a total of m free variables. Okay. So, for one free variable it being not in row I, the probability is this. So, for the all the m free variables, and the variables are chosen independently. So, the probability that none of them is in row I is 1 minus 1 over log n to the power m, and this quantity can be shown to be greater than 2 raised to the power minus m by log n. Okay. Okay. Now, what is m? M is 2 log n log n. So, if I just substitute that value, I get 2 to the power minus log n, and 2 to the power minus log n is equal to 1 over log square n. Okay. No, there is a 2 over here. So, there is a 2 over here, that is why I get 1 over log square n. Okay. Now, the probability that none of the free variables is in row I. Okay. Now, I want to argue what is the probability that none of the free variables occur in any of the. So, what is the probability that two to the power minus m by log n? Yes, yes. Okay. Now, what is the probability that there exist a row such that none of the free variables is in that row. Okay. So, basically this is for a fixed row. Now, if I take a union overall, so what is the, if I look at what is the probability that there exists a row such that the same condition happens. So, I will take a union bound. So, the number of rows are log n. So, this quantity is greater than or equal to log n times 1 over log square n, which is equal to 1 over log n. Okay. And now, we will use the fact that 1 over log n is greater than equal to half for n, actually for n bigger than 3 itself. Okay. So, this quantity is greater than half for large n of n. Okay. So, what have we got? That there exists the probability that this happens is greater than half. Okay.
Should the sign be in the other direction, and then we will say that for all rows there exists some free variable is at least one.
Huh?
If the sign in the last inequality should be in the other direction, and then we will say that the negation of that, which is that each row contains at least one free variable, is at least one.
So, if I am applying the union bound, so union of all these events, the probability of the union is okay. So, it is less than or equal to, yeah, it is less than or equal to the probability of the individual events. Yeah, so these are the individual events. So, yeah, you are right. Yeah, actually 1 by log n is less than or equal to half, true. Yeah. So, now what do we want? So, the probability that the negation of this, as you correctly said, that every row has a free variable is negation of this. So, it is less than or equal to, or it is 1 minus of this. So, it is less than or equal to half. So, and that is what we want. Okay. So, therefore, and now what does this mean? This means that, well, in this restriction, so I have restricted the variables, and now every row has at least one free variable, okay, and that occurs with probability so much. Okay. So, now no, so greater than again, sorry. So, that was less than, so this will be greater than half. Okay. So, therefore, the restricted function can still compute we are computing y star here, y star with high probability, okay, because every row has one free variable. So, what is the, so now we will just look at, we will use this size bound. So, we know that expectation of L A n star is greater than or equal to half times the size bound that we consider n over log n. This is the probability and this is the size. So, I mean the smallest formula has I mean the smallest formula has size at least this much. So, on an average it will have at least that much. Okay. But now, so this is one direction, but what we have by Subotaevska's theorem is that expected value of L A n star. So, if you look at a expectation sigma in R n m, okay. So, this has a bound of n by m whole to the power 1.5, I am sorry, m by n. So, this is just applying Subatovskaya's theorem, and now we just combine both these equations, and what we get is that L of A n star is greater than or equal to well, half n by log n minus 1/3 times the reverse of this n by m to the power 1.5. Okay. Now, if you look at this term over here, okay, so what does the numerator contain? So, I mean 1/3 well, this is just a small term. So, 1/3 of n by m to the power 1.5, that is a small term, I can just leave it out. But if I multiply n by m to the power 1.5, so okay, what is m over here? We can substitute for m as well. So, this is equal to half n to the power 2.5 divided by log n times 2 log n log n to the power 1.5 minus 1/3. Okay. N by m to the power 1.5. Now, if you look at this term, this is actually the dominating term over here, okay, and what we have in the denominator is something that is smaller than it is basically smaller than n, one can show, right, because it is I have log n and then 2 log n to the power 1.5. So, this term can be is asymptotically smaller than n. Okay. So, this we can write as being equal to omega of n to the power 2.5 minus small o of 1. Okay. So, this is the proof, and actually one can show quite easily, one can show that there also exists an upper bound for this function, an n cube upper bound for this function. Okay. So, that I will just give as an homework. Okay. So, exercise. Show that L A n is in order of n cube, and in fact, if you construct the formula a little cleverly, you can also get an upper bound of 2.5. Okay. So, basically this n to the power 2.5 is in some sense a tight lower bound. Okay. So, modulo of course, this small o1 factor, but it can be shown that there is an upper bound of n to the power 2.5 as well, but n cube is quite easy to construct. Okay. So, you can try that. Okay.